All right, here's another Sasquatch Hands video for you. We are going to be assigning R and S designations to different stereoisomers. So make sure that you view the previous video lecture that was all about enantiomers and stereochemistry and chirality, because we're going to be building on a lot of those ideas today. This R and S designation is a really important skill for you to be able to do, and it depends on your ability to kind of see things in 3 dimensions. So as always with these topics, it's really helpful if you have little model kits right here. So I just built a pretty simple compound. This may be the first time you've ever seen something like this, but that D is a deuterium. And one thing that also is going to help us out a lot, instead of building the entire model, really we're only going to build the stereocenters, right? And so sometimes you'll see like an asterisk next to a stereocenter or something that looks kind of like that, or an asymmetric carbon, right? A carbon bonded to 4 different things, which is what gives rise to most chiral compounds. I built models of both of these enantiomers here, and what we're going to do is to assign R and S designations to them. It doesn't really matter what R and S stand for. R is rectus and S is sinister, which is from the Latin for right and left. And there's some really particular rules that we got to make sure that we follow. One is that when we assign this thing, we always have to orient our lowest priority group behind the plane of the paper. And I'll show you how to assign priorities in just a second, but if you look at that hydrogen, that is the lowest priority, and you'll notice that it is a dashed wedge, right? It's going backwards. So in other words, as we're looking at this structure right here, I've got my fluorine kind of facing towards me, right? That's coming towards me, the solid wedge. The hydrogen's behind. This blue thing is going to represent the deuterium. And then I've got a methyl group over here that I, of course, didn't put any of the hydrogens on. Same is true over here, right? We've got that H positioned behind the plane of that paper, or going away from us, and that fluorine's kind of coming up at us. And that's actually the most important step of you guys being able to assign R and S properly. And the reason that I know hydrogen is the lowest priority group, and maybe I'll write with this dark pencil and see if we can see it, is that the hydrogen is assigned a priority of 4. I guess you guys can't actually see that. So I'll switch over to this. That hydrogen being assigned a priority of 4 means of the 4 different things that are bonded to that asymmetric carbon, it is the lowest priority, and that is because it is the lowest molecular weight. When you look at the periodic table, you basically go from your asymmetric carbon, you go out to the 4 different groups that are bonded, you look at whatever atom that is, and you're going for the lowest molecular weight. And in the case of organic chemistry, it's often a hydrogen, right? And we want to make sure that that is projected behind the plane. Okay. Well, we're going to assign priorities to all the rest of these. And of course, we're going to go by molecular weight. So you can look at the other groups that are assigned here, and we can see that fluorine is the heaviest on the periodic table. Carbon, which is actually the thing that's bonded there, right? This is going to be considered the second priority. That is a 2, believe it or not. Deuterium, right, because it is simply a proton with an extra neutron in the nucleus, that is going to be assigned a 3. It is higher priority than hydrogen because that hydrogen just has a molecular weight of 1. So deuterium with its 2, fluorine with its 19, and carbon with its 12 is how we decide these priorities. So the question is, what do you do with all these numbers? Well, it turns out if you grab a model kit and you position it properly, right, it should be positioned like this with hydrogen behind, you'll notice that if we kind of follow the numbers here, let's see if I can do it somewhere that you can see it, right? I've got a 1, a 2, and a 3. And if you follow that, follow my Sasquatch fingers here, you'll notice that that 1, 2, 3 pattern follows this counterclockwise pattern. It turns out that this is in fact an S absolute stereochemistry, right? Because it is going counterclockwise. So we are going to assign that thing an S. You would call this the S enantiomer. The other one, if we've done everything correctly, if you see like the mirror image of an S, it sure as heck better be an R. So let's make sure of that. We'll assign it the R and just hope that it's right. We've got a fluorine 1, hydrogen is 4, carbon is 2, and deuterium is 3. And when we hold this sucker up, then we position it properly. Hydrogen's behind, fluorine's coming out at us. We've got a 1, 2, 3, and in fact that is clockwise, right? Which is rectus, or R. And this is something we're going to do for every single asymmetric carbon. It turns out that it's much easier if you guys have a model kit. You can assign it according to what you see in the three-dimensional representation right here, but it gets a lot more difficult. And it's commonly the case that if you kind of play around with these two little groups and you don't show them exactly like I have, that sometimes you can kind of screw with your own mind, and looking at something that's flat, you'll actually get the wrong designation. So one of our major homework assignments, and it's going to be coming real soon, is going to be assigning all kinds of different RNS based on like different projections. We'll see Newman projections. We're going to learn something on Monday called Fisher projections. You're going to see like realistic perspective like this. We're going to see sawhorses, right? So all of those things are going to come to play. But for now, let's just kind of build the picture a little bit more slowly. And so what I'll do is I'll kind of show you how something that contains an asymmetric carbon, and what you have to do if it happens that group, that lowest priority group, isn't in the proper orientation. Here's another compound that'll hopefully allow us to kind of kill two birds with one stone here. So first of all, you'll notice that the hydrogen is projected out at us, right? So the lowest priority group is actually not positioned properly. So let's just label that as a 4. It's probably not going to be surprising to you that chlorine is the heaviest of the other two there, so let's just give that a 1. But what you'll notice here, in terms of assigning priority to these two things, if we look at the asymmetric carbon and go one atom out, you'll notice that they're both carbons. So what do? Well, it turns out this is where we're going to use what's called the Kahn-Ingold prelog convention, and we're going to be doing this quite often. And there's a fun little name, KIP, right? So the Kahn-Ingold prelog system is going to be a really dogmatic system that we're going to apply anytime we need to assign either R or S, or eventually we're going to be assigning E and Z through the same thing. And the thing to keep in mind is it's the first point of difference where you list everything else bonded in descending molecular weight. What the heck does that mean? Well, let's go to this situation that we have right now. Right? We've got 2 carbons. We know that's that nothing wins at this point, right? So what we're going to do is we're going to recognize that atom, and the fact is that each carbon is going to be bonded to 3 other things. So we're going to call both of these things a C, and I put, those are little commas, right? And we're going to, let's move this for just a second. And we're going to list off in descending molecular weight all the other things that are bonded to that particular carbon. So you'll notice that it's got 2 hydrogens, and it also has a carbon that it's bonded to, right? And so carbon being heavier than those 2 hydrogens, this is what's called a CHH carbon in the Kahn-Ingold prelog system. You look over here, this guy is bonded to all hydrogens. And so, as I said, we look for the first point of difference in descending molecular weight, and you'll notice that our decision is made pretty early, right? We're now comparing that carbon that's bonded there to a hydrogen, and so this guy right here is actually going to be the second priority, and this will be the third priority. Okay, so let's take a look at our model kit here. And just to make things easier, I put a little bit more detail into this guy. So obviously this blue dude that's the chlorine, right? That's the highest priority group up there. There's the hydrogen projected towards me. And I also put in a little bit more detail so that you can see those 3 hydrogens of the methyl group that's projected behind the plane there. And so let's first assign R and S according to the structure that I hold in my hand here. And then we'll do it for the flat structure. Right? And so we know that we have to position that hydrogen group away from us. Right? We have to sight through the carbon to the lowest priority group. So I just did a flip. There's the hydrogen on the other side. And now we have to do the same thing we did previously, where we look at our highest priority group, which is right there. Our next priority group is that ethyl group over here. And then, of course, you've got the methyl group. So if you follow my Sasquatch hands, 1, 2, 3. 1, 2, 3. So you'll see that we, in fact, have a clockwise orientation. So this, in fact, ends up being an R stereoisomer. That R stereoisomer, you should be able to look at the flat thing and also assign the priority. So one trick, by the way, I was really bad at this, and it's really easy for especially people that have any kind of spatial reasoning or artistic ability, but I was not one of those people. So what I eventually recognized, even though it took me an embarrassingly long time, if the lowest priority group is projected out at me, I can simply follow the 1, the 2s, and the 3s, right? And so there's the circle that it makes. And if the if the lowest priority group is pointing out at me, I just switch it, right? So it turns out that I would have ended up with the correct R. Those of you guys that are into like geology and things like that, that's I think is called the, or at least based on what the Coriolis effect is based on, right? This idea that like if you watch something spin from the top and you go to the other side, it looks like it's reversing directions. Not very easy to show in this kind of video lecture format, but I wanted to show you a couple of things about this. So that is definitely an R. And you know, one of the things that we'll often have to do is we'll have to kind of rotate these things on a flat piece of paper. So your homework will probably have you guys do a couple of those manipulations, just so I'm confident that you can do them. It's going to be very common that we'll end up with you know, some sort of stereoisomer, and we'll have to show the enantiomer. Well, it turns out that we could, of course, reflect this in a mirror plane to figure out what the enantiomer is. But it turns out that there's this kind of clever little thing, is that if you want to draw, let's say, that the enantiomer of this compound, the S, all you have to do is interconvert any 2 of these groups. So you could switch this H and that ethyl group, that H and that Cl, that H and that CH3. That's probably the easiest to see, so I'm going to do that. But that's a really quick way of drawing the what ends up being the enantiomer. So all we do is we flip those 2 groups and keep the other 2 groups the same. I guess that's pretty important that you keep those other 2 groups the same. So it turns out when you assign this thing, we hopefully will be able to assign the S pretty easily. We got 1, 2, 3. So we've got a counterclockwise pattern, so that guy is definitely an S. So these 2, and you'll notice if you just kind of came across these, it might be kind of difficult maybe to recognize that they're enantiomers. And so it's really helpful. R and S is actually super helpful for deciding whether things are enantiomers or not, right? And so like we might see a problem where we see something like this and recognize that there's a methyl group, an H, a Cl, and an ethyl group. And then we see something else that has those exact 4 same things bonded, that same kind of asymmetric carbon. It turns out if you're really good at assigning R and S, you're going to be able to determine very quickly whether it is truly an enantiomer or some other, or the same compound, or some other relationship that we'll talk about eventually here. So let's just kind of see this, right? Like I'm just going to kind of blindly, I'm not going to think about it in any way. I'm just going to throw together a bunch of groups, including these 4 groups. And like I said, it might be easier for some than others. And hopefully I don't fool myself. Let's just say that I draw this, and I want to know, really quick, is that which one of these matches, right? Which one of these are enantiomers? Let's see if we can do it, right? Well, we've got hydrogen as the fourth priority group. We've got our chlorine here. We've got this is our 3, and this is our 2. And just on this little flat piece of paper here, I've got 1, 2, 3, right? And so it looks like this, but we have to make sure that that highest priority group is projecting backwards, and it is not, in fact, projecting backwards. So that means I have to reverse the direction I ended up with, right? And so this is, in fact, an R. And believe it or not, these are equal, right? These are just different, you can tell that I guess I just kind of rotated this thing around if you're good at seeing things in 3 dimensions. And then these are related as enantiomers. Okay, so I would definitely practice with this RNS stuff as much as possible. And of course, like it could be the fact that that lowest priority group is actually in the plane of the paper, in which case you kind of have to imagine yourself kind of sighting up and to the side or manipulating it in some other way. So I'm going to wait to see what you guys struggle with, and I'll address each one of your problems in office hours. You just have to make sure that you practice so you know what you struggle with. Okay, so let's now start with a compound that has 2 stereocenters, or I should say 2 asymmetric carbons, right? We've got an asymmetric carbon right there. We've also got an asymmetric carbon right there. Turns out once you have more than one asymmetric carbon or more than one stereocenter, things start to get a little bit more interesting in terms of relationships between compounds. So first, let's assign R and S to both of these. And one thing that I find really, really helpful, even though it gets kind of difficult to do with a big old Sharpie here, is I always like to put in the missing hydrogen, right? That hydrogen is often not shown. So let's do that. And assigning priorities in rings is another thing that we really have to be good at and practice a lot. So let's see. Yeah, let's see if I can get this pencil to show up a little bit better if I draw a little darker. Right? So let's start with this one. So we're going to take that H. We're going to know automatically that that is a fourth priority group, right? And now our job is to figure out which one of these is number 1. And so one of the things you'll notice as you look around here is you notice a carbon there, and a carbon there, and you say, oh man. But if you notice kind of quickly that this carbon is bonded to another carbon, that carbon is bonded to another carbon, this guy's obviously going to lose to that, right? And so this is that thing that we saw before, which is the CHH kind of carbon, and hopefully you can kind of see that. This carbon over here, right, that is going to be a carbon that has another carbon, an H, and an H. Boy, that is really tough to see. Sorry about that, guys. This guy down here is also, here, let's do a little arrow here, is a carbon with a C, an H, and an H. And what you'll notice is that at this point, right, these 2 carbons are still tied, right? We're still looking for the first point of difference, which will happen eventually if you keep going. And so we're going to go down here now, and we're going to say, well, that carbon is a CHH carbon, and then this carbon is actually a CCH carbon. And you can probably see where I'm going with this, is it turns out that that carbon ends up being the second, sorry, is that first? Yeah, that's the first priority group. Sorry about that. Yeah, we already have the third priority group over here. And then this carbon ends up being the second priority group. So what you can see me doing there is like I'm being pretty dogmatic about using my parentheses and listing things off in terms of the highest molecular weight first. What really confuses students sometimes is if they're not dogmatically following this, right? Remember, it's the first point of difference. Like for instance, up here, if I had like this, like imagine there was like a chain with like a big honking chlorine group or something like that. Well, it turns out that wouldn't play any role because we go one atom at a time to figure this out, right? So what does that make our circle? So we got 1, 2, 3. We've got an R. We make sure that H is in fact behind the plane, and it is in fact behind the plane. So we'll just hopefully put a little tiny R on this guy. Let's kind of do the same down here, and this time I won't insult your intelligence. I'll just go a little bit faster, right? And, oh, one thing I always like to do is erase. Of course, now that this pencil is so dark, it's really hard to erase, but we'll see if we can actually see anything. I should just redraw it. Yeah, the heck with it. Okay, so we got 4. We look at all these different carbons. This guy is a CHH. That guy is a CHH. This guy is a CHH. Right? So far, nobody wins. So we go to the very next highest priority group. That guy is a CHHH, which sounds like a loser to me. That's 3. Next guy here is a CCH. This guy right here is a CHH, right? So let's see, where are we right now? So that guy was the loser. This group ends up being, oops, number 1. Oh, yeah. This group ends up being number 1. This group over here ends up being number 2. All right, let's check my work. Right, that definitely loses. That guy wins over that. Okay, good. So now we're ready to go. We've got 1, 2, 3. Right, it's doing this. But that H is projecting out at us, so we got to reverse it. And that guy ends up being an R. So let's put that in there. Okay, so we've got what's called an RR stereoisomer. Okay, well, what could we do? Well, we could show the enantiomer of this, right? That would be, obviously called the SS. And I'm just going to follow that rule that you interconvert any two groups. So now I'm going to put the CH3 behind. And I'll leave the H off, even though it should be projected out. Sometimes you leave it off. This guy down here, that's going to be my ethyl group. And so when we went through and assigned this thing, take my word for it, this would end up being an S. That would end up being an S. And so these two are related in that they are enantiomers of one another. Maybe I should write that in, enantiomer. But you can probably see where I'm going with this. Well, what if the compound that I'm looking at just switches one of those asymmetric carbons? Right? In other words, this would be an SR enantiomer, or SR stereoisomer. Right? So what is the relationship between this guy that I just drew and both of these? It turns out that there is a relationship. It is called a diastereomer. And diastereomer is a trashy word, but we definitely know how to apply it. And what I mean by trashy is that in the scheme of stereochemistry, when you look at two things that are enantiomers of one another, that's a special relationship. But it turns out anything else that has the same connections between atoms that are not, let's say geometric isomers or not constitutional isomers, right? This guy is obviously somehow related to these other two, right? But it's definitely not an enantiomer. It's definitely not special in that, it rotates plane polarized light to the exact opposite direction and interacts with enzymes in a very different way. It turns out that this other thing called the diastereomer is related very nicely by structure, but its properties are completely different. If you viewed that video lecture where we talked about the properties of enantiomers, it turns out when those two enantiomers are alone, they have all of the same properties with the exception of the rotation of plane polarized light. It turns out that diastereomers have completely different chemical and physical properties from say, this stereoisomer. Okay, and so the interesting thing is that this diastereomer, I could obviously draw the other enantiomer of that, right? And that other enantiomer that I drew would also be a diastereomer of these two compounds. So that kind of relationship is pretty common, and keep in mind this is only two asymmetric carbons. You could imagine an enzyme, well, let's not go to an enzyme, right? But imagine that there is some compound, right, that has 4 different asymmetric carbons, some big thing, right? And you assign R, S, R, R. Well, it turns out that anything that is not the enantiomer, right, there is an enantiomer that you might expect is SRSS, right? Those two are enantiomers, but absolutely any other permutation combination is going to be a diastereomer. So like, for instance, R, 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 R is a diastereomer of these two, right? S, R, S, R, right? That would be a diastereomer of these two. So there's that kind of special relationship that exists between enantiomers, and diastereomers are just kind of they have to be included as another part of the party. Okay, so with that said, I would say it's probably a good idea to go ahead and try some of the homework. Definitely next week's homework is going to be a lot more of this kind of stuff, and really it's something that you have to practice. There's no easy way for me to just impart the knowledge without you practicing, and it really helps to kind of bounce questions off of me. So I hope to see you guys a whole bunch in those office hours next week. Okay, thank you much.